Hello everyone, I am Nikita Mahajan and I'm a research scholar from School of Chemistry, University of Hyderabad. Today I am conducting a problem solving session for the NPTEL course Ultrafast Laser Spectroscopy. First let some people join. I am giving a time of around 5 minutes so that the people join and or 2 minutes we'll start by that time. Yeah, so without wasting time, let's continue with this. So now I'll be sharing my screen for the display of questions. Okay, so first of all, ये ना presentation. Yeah. So, since ultrafast laser spectroscopy, this is one of the course which is taught by Professor Anindya Datta sir. And regarding this, we'll be discussing a few questions which some of you or most of you may have problems with. And in order to make the entire course easy, these sessions are conducted. So I'll be discussing around 10 to 12 questions which are the most important ones. Now, the first question will be the wave number of a transition from ground state to excited state is 20,300 centimeter inverse. What range of electromagnetic spectrum does this correspond to? The options given are infrared, microwave, UV visible and radio waves. Now, since in order to start with this question, first we'll discuss what is the entire electromagnetic spectrum and what are the ranges it covers. So, starting from the highest frequency, highest energy radiations to the lowest, this is in the decreasing order of energy, and like from gamma rays to when you go to radio rays, it this covers the different variety of electromagnetic radiations. The gamma rays is the highest energy electromagnetic radiation. Then comes X-ray. After that comes the ultraviolet radiation, which is the UV range. The third one is the visible ray. The fourth one is the visible range of light, which we can see. And after that comes the infrared, which is divided into far, near, infrared region. Then comes the microwaves, and further comes the radio waves. Now, in order to convert each, like in order to know which of the wave number or which region it corresponds to, here there are labeled regions as you can see in the picture. The first one is the gamma range for which the wavelength is in the 0.0001 nanometer. There comes the X-ray. So as you go from left to right, you will see that the wavelength is increasing, and therefore since we can see from the equation that E is equals to hc by lambda, you will see that the energy is decreasing. So in order to solve this question, I'll make you solve this question on a manually. So first of all we'll solve this on a screen. That is, if you know what is the relation between the wave number and the wavelength, we'll denote the wavelength by lambda, which is equal to the inverse of wave number, which is given by mu bar. Okay, now since the wavelength, its unit is in any terms, you can call it in nanometer. If you want to convert it into wave number, say centimeter inverse, so it will be inverse of the wave number. So the what you will get the answer, that will be in the nanometer inverse. So here, as you can see, in the present, as you can see, what we are given is 20,000 centimeter inverse, which states that this is probably they are talking about the wave number thing. So in order to convert the same to nanometer, we'll take its reciprocal. Okay, so I think the the writing is a bit small, so we'll clear all of this and then convert. So first of all, what we are given, that is 20,300 centimeter inverse. Okay, so in order to convert this, we'll do its reciprocal, 20,300. So when you do its reciprocal, 1 upon 20,300 centimeter inverse, you'll get the answer which would be around 4.926 into 10 to the power minus 5 centimeter. Why? Because this entire thing 20,300 was in the unit of centimeter inverse. So when you do the reciprocal, you will get the same answer. Now, since this is in centimeter, it would be better if we convert this entire thing to nanometer. So if you convert this, as we know the relation, 1 centimeter is equals to 10 to the power 7 nanometer. Okay, now since it is 10 to the power 7 nanometer, in order to convert this, we'll convert this 4.926 into 10 to the power minus 5 multiply by 10 to the power 7. Okay, now if you convert this, you will get the answer 4.926 into 10 to the power 2. Okay, and this, what will be the unit? The unit will be in nanometer. Although the writing is not very proper, but I'll just put the answer in a box, and if you just convert it and remove this power, you will get the answer. The answer would be 492.6 nanometer. Okay, so this will be our answer. Now half of our question is solved. Now what we need to see is which region does it belong. So if you see the entire electromagnetic spectrum, you will see that in the visible range, which is slightly from 380 nanometer to 740 or something nanometer. So since what we got the answer was around 492.6 nanometer, our light would lie in the visible range. So this was the thing. So the wave number of transition from ground state to excited state is 20,300 centimeter inverse. Now what region of electromagnetic spectrum does this correspond to? The answer for this will be UV visible range. Okay, so if anyone has any doubt in this question, please just ask. I'll give you a time of 30 seconds. If you have any doubt, like how did I solve the question, you can just ask the any query regarding this. So does anyone have any doubt? Okay, no doubt. Okay, thank you, Adrija. Now the next question is, as per Beer-Lambert's law, on which of the following factors does absorbance depend? Okay, so the options given here are extension coefficient, color, distance that light traveled through the sample, and concentration. Now, since we'll discuss each and everything in detail, the first thing here is what is Beer-Lambert's law. So Beer-Lambert's law is, for a given material, the absorbance is the amount of light which it absorbs, depends on the sample path length and the concentration. Now what is this sample path length? Sample path length is, suppose you consider a cuvette thing, okay, and okay, so I'll explain this in detail, is equals to epsilon CL. So for the same, I sorry for the inconvenience, but we have to go to another thing, which is this. Okay, so we'll just erase all the things. Okay, so for this I'll just write the equation for given according to Beer-Lambert's law is A is equals to epsilon CL. Okay, now here A stands for the absorbance, epsilon stands for the molar extinction coefficient, C stands for the concentration, and L stands for the path length. What is this? Suppose you consider a cuvette, so the distance covered by light when it passes through the sample. This is the path length L. Generally it is taken as 1 centimeter or something. So basically the unit for L is centimeter or the unit of length. For C the unit will be mole per liter, and for epsilon, since the absorbance has no units, for epsilon the unit will be, wait, let me show you how to calculate this, mole per liter. Okay, so mole per liter it is, and since it has no unit, when all these things, the unit for epsilon will come to be liter mole inverse centimeter inverse. Okay, so this is the unit for absorbance. Now I'll just clear because this is just too much scribble thing.
हाउस ऑप्शन ऊपर में सर न्यूट्रल.
Okay, so now here as you can see, for a given material the absorbance depends on the path length A epsilon CL. So clearly the answer which we'll get is the where epsilon is the extension coefficient, so this also we get in the equation. Distance traveled by light, which we could see that was L, and concentration is C. So clearly the option B will be our answer, that the absorbance does not depend on the color of the solution. Okay, now related to this is just an equation which we'll be using later in some questions. That's why I've given some extra information. Like the absorbance can also be calculated by the relation A is equals to log I naught by I. Okay, here I naught is the intensity of the incident light which we are incidenting on the sample, and I is the intensity of the transmitted light. Now this can also be given into several other relations which we will be discussing later. The third question, if someone has any doubt regarding this, please ask. I'll give you a time of 30 seconds so that you think enough, and then we'll discuss on this. No doubt. Okay. Let me just check if someone has tried sign in. Okay. Okay. No one else is trying. So let us go to the question number 3. The question 3 is, if a fluorophore, what is a fluorophore? We'll discuss this. Absorbs in the range of 375 nanometer. Its If a fluorophore absorbs in the range of 375 nanometer, its emission maxima is expected to be. So the options given were smaller than 375 nanometer, greater than 375 nanometer, 375 nanometer, or not enough information. So first of all, what is a fluorophore? So fluorophore is something which shows fluorescence or undergoes a radiative emission. Now this fluorophore can also be is also synonymous to another term, that is luminogens, and or something which shows fluorescence or which is light emitting. Okay, so in order to discuss this in detail, first we'll go to the Jablonski energy level diagram. So this is just the Jablonski energy diagram. Now for any system, if you consider this is the initial setup, like if you want to study any system, suppose you want to study a benzene molecule itself, what you will see is there is a ground state for a molecule and there is an excited state. Suppose the electrons are two paired enough. Okay, so this I'll just explain using my diagram. So suppose this is the state, this is the ground state. Actually this is the ground state, and the sub levels are the, you can say, the vibrational and rotational energy levels. Now in this system, if you provide any sort of energy, suppose it absorbs in the UV range, then because of the absorption it will reach to a higher energy state. So ground state, I am denoting it with G and the excited state with E. Okay, now suppose this is a pair of electrons, and since they are paired, this is called to be the singlet state. S is equals to 0 because the total spin is 0. Now after gaining enough amount of energy, or after the supply of energy to the system, this will reach to a higher energy excited state. This excited state is E. Okay, now this excited state E, our one of the electron has reached to this state. Now from this state, what are the various processes that are involved, because of which it will again reach to the ground state. So as you can see from here in this diagram, this excited singlet state refers to suppose this is in the two electrons have the opposite spin, and therefore the total spin of the system is 0. So after this absorption to the singlet state, it can dissipate its energy to different forms. The first one is internal conversion. Now internal conversion, what does it state? Like from the higher singlet or the excited singlet state, it reaches to the ground singlet states or the other excited states. In this diagram, when you will see, there is S2 and S1. There are further 5, 3, 2, 1. These are the vibrational energy states. In S1, similarly in S1 there is one the excited singlet state. Along with this, there are another vibrational energy states. Okay, so The green arrow, what it shows is the excitation using by any range of radiations, we can say UV range. Now how does it dissipate? The first one is internal conversion, when the electron or when a system from the higher energy state comes to the lower singlet states itself by a non-radiative emission. In non-radiative, what does it mean? Like there is no emission of light through the process, or through the vibrational relaxation. You can say vibrational relaxation, since there are a lot of molecules, it vibrates and relaxes to the lower excited state. Now after this internal conversion, there is one more option, that it can reach to another excited triplet state. Now what does this triplet mean? So this triplet means that, like from this state, if it goes to this, suppose this to okay. Now here is some state, that is the triplet state. So from here it reaches to this state, and there is a change in spin accompanied. So since when you talk about these two electrons, both are in the same spin, and therefore if you calculate the total spin of this system, it comes to be 3. Because if you calculate the total, it comes to be 1 by 2 plus 1 by 2, and this comes to be 1, and the spin multiplicity, which is 2s plus 1, will be calculated, and therefore it will be 2 into 1 plus 1, and it will come to be 3. So therefore this state is called a triplet state. Now the electron has is removed from here, and it has come to this state. This is the excited triplet state, as you can see. So, and the earlier one was a singlet state. If you want me to deduce how we could call it a singlet, so suppose this is in this spin, so this is plus half, this is minus half, so this is half, that is minus half, the total comes to be 0. And therefore if you calculate the total spin multiplicity, which is 2s plus 1 or 2ms plus 1, it is 2 into 0 plus 1, and therefore it is 1. The total will be 1, and that is why that was called the singlet state. Okay. Now along with this, to the excited okay, sorry. Yeah. Now since it has maybe it can undergo from excited singlet state, it can come to an excited triplet state, and when this conversion occurs, this is called as inter-system crossing. Why so? Like this is a term given to it, and the second thing is, this is also a non-radiative emission, and the third one is so what are the processes? Non-radiative emissions we discussed. The first one was internal conversion, and the second one was the inter-system crossing. So these two processes are the non-radiative relaxation type of processes which a molecule undergoes after excitation. What is the time range? So for the absorption, it takes around 10 to the power minus 15 seconds, and further this, within a fraction of seconds, which is in the range of 10 to the power minus 14 or minus 11, it will undergo these processes. The first one is internal conversion, or you can say the inter-system crossing. These processes are very very fast processes. Now along with this, what are the other things which can happen? So as you can see, what the red arrow denotes, that is the fluorescence. So what what was asked in the question is if a fluorophore. Why I am discussing this in detail? Because I have to explain you how or why the thing is, why the answer has come, why the desired answer will come. So this fluorescence is a radiative process, that is, whenever you excite the molecule, it will relax by radiating some amount of light. Light is in the form of wave or particle nature. And the third one can be quenching. And how does this quenching, what are the processes? Like the molecule can interact with the neighboring solvent particles, solvent molecules, and therefore the energy can be dissipated, or the vibrations, rotations, or the other processes, or it can collide with the other neighboring molecules of the similar kind, and this is how the relaxation will occur. So these are the entire processes which are covered and which are explained by the Jablonski energy diagram. Now what our question was, if a fluorophore absorbs in the range of 375 nanometer, which is in the range of, you can say, UV range, its emission maxima is expected to be. The why I explained you is, as you can see, the excitation is denoted by a green arrow, but the fluorescence is denoted by a red arrow. If you calculate according to the energy level diagram also, the green arrow is requires higher energy, while the fluorescence it is emitted at a lower energy. And if you talk about the energy and the wavelength relation, you will see that you will just a second. You will see that E is inversely proportional to lambda, or the wavelength. So if we are talking about 375 nanometer, okay, if we are talking about 375 nanometer, something that corresponds to a lower energy should have a greater wavelength. Okay, so since, okay, just a second. So if you are talking about 375 nanometer, if E is less, lambda will be more. So if the emission is occurring at a lower energy, then the wavelength is desired to increase. Now from the question we are able to solve this. If a fluorophore absorbs in the range of 375 nanometer, the maxima is expected to be greater than 375 nanometer, and this is what we see in the absorption and emission spectrum. If any one of you is has any time saw an absorption and emission spectrum, you will notice that there is a shift in the absorption and emission. And if you see the diagram or if you see the spectra for any compound, say if the absorption is somewhere in 375 nanometer, the emission will occur with a gap, and this shift in the emission and the absorption, this is called the Stokes shift. What is it called? It is called the Stokes shift. And why is this happening? Why is the emission? Because ideally if a system absorbs something, ideally if it absorbs and reaches up to some level, then it should emit the same wavelength of light. Now where does that extra energy go? Like where does that our energy go? So that the Jablonski diagram, it is enough to explain the entire thing, that there are many processes, internal conversion or intersystem crossing or the radiative fluorescence or phosphorescence, which are responsible for this red shift to occur, and that is why our answer for this question will be greater than 375 nanometer. Now there is one more process along with this which which maybe I missed to explain, that is the phosphorescence. So This thing we have been studying initially and long time back also. What is this phosphorescence? So sometimes what happens, if the electron has reached to the excited singlet state, it may emit from the same excited singlet ground state to the ground level, or it may go to the another excited triplet state and may reach to the ground state, emitting or through a radiative pathway. Now when it go from the excited triplet state, if it emits the radiation and comes to the ground state, this process is called as phosphorescence. Why are the two terms different? How can we visually distinguish them? So for the fluorescence process, that is for the fraction of seconds, it has a very smaller lifetime. As you can see, it is from 10 to the power minus 9 to 10 to the power minus 7 seconds, while the phosphorescence, it lasts for a longer time of 10 to the power minus 3 to 10 to the power 2, that is around 100 seconds. So initially, if you see any substance or which is a fluorophore which emits something like fluorescence, you will be able to distinguish between the fluorescence and phosphorescence visually. There is no problem, like if you cannot distinguish between the two. Now along with this, there is some other thing which I wanted to discuss is that is the Kasha's rule. Now if you study about any system which is a fluorophore, which undergoes these radiative emissions, there is a rule that whenever any molecule it is excited to any excited state, after reaching to the vibrational zero level of its excited state, then only it will start emitting. It will not happen that from such an higher excited vibrational state it will start to emit. So this is the Kasha's rule for this emission, like radiative emission. Now the emission with change in spin multiplicity, what is it called? So earlier, as we discussed in this diagram, if any one of you may give this answer to me, because as I have discussed this thing initially only, like emission with change in spin multiplicity. So first let me tell you what emission is. So what we discussed here is the radiative, fluorescence and phosphorescence. These are the processes which are covered under the emission thing. These are the processes which come under the category of emission. If a molecule emits light in the form of light on excitation, then it is said to be a fluorophore, or it is said to emit something. What is the change in spin multiplicity? So change in spin multiplicity, again I'll give you a hint, as we had discussed. Multiplicity multiplicity is, suppose you I say you a system with these are the two, suppose I talk about any system in which all the electrons are paired. So these are the set of electrons which are paired. So if you want to talk about the multiplicity, initially these two electrons each has a spin of ms is equals to half. Okay, now if it is this way, it is plus half, and if it is the anti-parallel, this is the said to have a spin of minus half. If you want to calculate the total spin of this system, you have to add up the individuals, where is ms 1 plus ms this of the second electron. So the total will be so the total will be 1/2 plus minus half. Okay, got it. Now plus half plus minus half equals to 0. Okay, so for this, if you want to calculate the spin multiplicity, which is calculated by 2s plus 1 relation, since this is the total spin we calculated, this is equal to s, and if you want to calculate the spin multiplicity, which is 2s plus 1, so here it comes 2 into, here what did we calculate the s, that was 0, so 2 into 0 plus 1, and this comes to be 2 into 0 0 plus 1, so here this is called the its spin multiplicity has come to be 1. Okay, now the other thing, suppose I had the system which had electrons which were paired. Now suppose I have a system where the electrons aren't paired. They are in two different orbitals like this. Suppose the system is like this. How do we calculate then? So in order to calculate that multiplicity, for each, as I told, if it is in the parallel way, the multiplicity in total will be equal to, so the multiplicity in total will be equal to ms is equals to half plus half. Okay, so this will be equal to 1. Now if you so this is the total spin what we calculated. If you want to calculate the spin multiplicity, it will be equal to 2s plus 1. So it will be equal to 2s plus 1, and therefore so 2 into s means 1 plus 1. Just a second. Yeah. So it will come to be 3. Okay. Now what our question was, emission with change in spin multiplicity. So as you can see from the diagram, emission with change in spin multiplicity will be from the ground state to the excited singlet state. For the excited singlet state, the multiplicity is 1, and for the excited triplet state, the multiplicity was 3. So from 3 to the ground state means the singlet ground state, there is some change in spin multiplicity which is from 3 to 1, and that is why it is the only process which has change in spin multiplicity. So first of all, what was the emission? So emission, the two processes, fluorescence and phosphorescence, these are the processes which involve which come under the category of radiative emission when the system decays. And the second thing is, change in spin multiplicity happens only with the system when it is the case of phosphorescence. Okay, so this is the answer for this question. Now we'll come to question number 5, which is a laser spectrometer has a superior resolution than an ordinary spectrometer because laser light is pulsed, coherent, highly monochromatic, and intense. So yeah. So a laser spectrometer has I'll just repeat the question. A laser spectrometer has superior resolution than just a second. A laser spectrometer has superior resolution than an ordinary spectrometer. Now, what is this spectrometer and what is this laser spectrometer? So, first of all, as in the first starting lectures of this series of ultrafast laser spectroscopy, what we studied was what is a laser and what is the laser spectrometer. So, this depends on the source of light what you use. If you use a spectrometer which has a laser source, and that is a laser spectrometer, and if you use some another source which is the ordinary spectrometer, that is which has an ordinary source of light, which may be tungsten filament lamp, deuterium lamp, or else extra, these are called these come under the category of an ordinary spectrometer. What are the specifications of a laser spectrometer which are different from an ordinary spectrometer, and how is laser light better? This we'll discuss later in the coming slide. So first of all, properties of a laser. Now, what is a laser first of all? So the full form of laser is light amplification and stimulated emission of radiation. So after what how is this different? Well, like suppose if you you consider a system where what you have done is just a second. Yeah. So consider a system where you have just excited the electrons to a higher energy state. This is in the simplest language in which I could explain what a laser is. So first of all, suppose this is the ground state. You have excited the electrons to a higher energy state, which is this, maybe this, or a triplet state. Now, if the entire population has been collected to this higher energy state, if you what a laser does is there is a population inversion, because initially according to Boltzmann's rule, if you consider whatever the situation is, however you excite, the ground state will have a higher population, ground state population, like N naught may be the ground state population and Nj may be the population of the excited state. So according to the Boltzmann rule, however you excite the initial population, the population of the ground state will always be greater than the excited state. So here what they do is practically they do a population inversion sort of thing, like the excited state has a higher population compared to the ground state. Now with a little bit of stimuli, the entire population or all the electrons, they come up all of it together to the ground state. Since you know that the intensity of any light emitting is directly proportional to is directly proportional to the population of that particular state, and that is why the light which comes to the or the light which is emitted is highly intense, and since all of them they are situated, they correspond to only one wavelength of light. Now, these are the properties of laser. The first one is monochromatic, means all the wavelengths which are the part of that all the wavelengths, they correspond to the same wavelength of light. They are not changing. Like suppose if you want to consider 375 nanometer, they'll be, all the wavelengths will be of 375 nanometer itself. The second thing is coherent, like they are in the same phase. Actually, I have just constructed this a small animation diagram. Suppose if you consider light in the form of a wave, you will see this is the this is in the form of the crest and trough. So here all the wavelets will be in the same phase. There will be no phase angle change in them. The third point is it is collimated, that is this small picture. This denotes that they are in the collimated, or they are not spreading, they are all in the one direction. Suppose if you consider a spot that is spherical, in the ordinary light you will see it is in all the direction, because of which its intensity is a bit reduced compared to the laser light. In case of laser light, suppose if you have a pointer and just lighten it or switch it on, you will see that if it is in the form of a sphere, that sphere is of its size itself. It is not just spreading, or it is not very enlarged or something. It is of the same size. And the fourth thing is highly intense. Since I explained you that the intensity depends on the population of the excited state, and if you consider that according to the entire principle which I discussed a few seconds back, since all the electrons from the higher energy state, they come all together to the ground state, the intensity is quite high compared to the ordinary light. So what are the advantages of this thing? The first one is, because of the monochromatic city of the light, you will be very specific about the purpose, or if you want the light which is of 380 nanometer, in that case you will get a light which is really of 380 nanometer. The second thing is, if it is collimated, it is not spreading, it will be affecting its intensity, like it will be highly intense. And the second thing is property of an ordinary light. So if you consider the ordinary light, suppose you consider the normal lamp what we use, it is polychromatic. Polychromatic stands for if it contains the light of variety of wavelength, so which is opposite to that of the laser light, which has only one wavelength of light. It is polychromatic, which has a number of wavelengths of light. For example, if you take 380, it will not be exactly 380, it will be from 370 to 390 something, or more than that. Now non-coherent means all the wavelets, they are not in the same phase. There will be a lag of 90 degree or somewhere less or more than that. The third is non-collimated, which means it is spreading. As you can see from the picture, if there is a source of light, it will not move to the only one direction, it will be spreading through all the direction, and that is why the fourth reason, it will be less intense compared to the laser light. So if we switch to the question, the laser spectrometer has a superior resolution. Why is it? Because now any one of you, what do you think may be the possible reason for this? What can be the possible reason? If this is the property of a laser, if this is the property of an ordinary light, what can be the possible reason? Why is a laser spectrometer more superior than an ordinary spectrometer? So what I think is the reason, although we studied coherent can be the reason, intense is the reason, or pulsed is maybe the reason, but pulse cannot be the reason. So as far as I can say is highly monochromatic is the reason. Why? Because if you consider a system, suppose you want any solution, if you want to illuminate it or take its absorption spectra, and if you supply, if the source of light which you incident on the particular solution, then the like the light which you incident, that should be very particular, so that you get the absorption in the particular range, or so that you can precise, you can be like you can get a precise reading about what the actual absorption, or in which range the absorption of the particular solution lies. So for this, highly monochromatic is the most probable answer. If anyone has any doubt in this question, just ask once. Okay, so now we'll switch. Is my voice audible to everyone?
Yes, it is audible.
Okay, thanks. Now we'll come to question number 6. From the classical theory of thermodynamics, the fastest possible chemical process is expected to have a rate constant of the order. So I'll just repeat the question. From the classical theory of thermodynamics, the fastest possible chemical process is expected to have a rate constant of order. Now this question is for this question we'll go to some equations through which we'll calculate what the rate constant will be. So first of all, what we'll go to, for this I need a pen. So okay, now first of all we'll go to what is the relation, or which relation we'll use to calculate this. So first we'll what I want to say is, first we'll use the van 't Hoff's relation, van 't Hoff's equation, van 't Hoff's equation. Okay. Now, so what the van 't Hoff's equation is, as some of you may have studied in chemical kinetics, that the van 't Hoff's equation for the rate constant calculation is given by K is equals to A into e to the power minus E naught by RT, or E naught, it can be EA, you can say. Now what is this EA? EA is the activation energy. Okay, R is the gas constant, and T is the temperature in Kelvin. A is the Arrhenius constant and K is the rate constant. If you want to discuss the units of each, now activation energy, its unit will be kilojoule or joule per mole. Okay. Then R and T. So unit of temperature will be Kelvin, and or you can say for the unit for activation energy will be joule per mole. So then comes the unit of R, it will come to be joule per Kelvin per mole. Now if you calculate, all the units will be cancelled, joule, mole inverse, then joule per mole. of this. I am talking about this equation initially. R is the gas constant, its unit is joule per Kelvin per mole multiplied by Kelvin. So mole to mole it will be cancelled, Kelvin inverse to Kelvin, and joule to joule. Sorry. Okay, just a second. So joule to joule will be cancelled and will be left with nothing. So this entire becomes unitless, and therefore the unit of K will be in the, or A will be in the terms of rate constant. It can be second inverse if it is a first order reaction, or it can be mole per liter per second if it is a zero order process, or etc. That you can calculate. Now, what is the relation between what I was talking about in the question? That was, what was the relation between the fastest chemical process and the rate constant order? So, first, if you get a hint from this question, if what will be the fastest chemical reaction, and how can be the reaction be fastest? That is, or how fast is the reaction, that we get to know using the rate constant thing. And like, if the rate constant is the highest, then the rate of the reaction will be the highest, because anyway the value of rate constant determines or just states us how fast or slow the process is. So if K is the rate constant, if you see this entire equation, when will be the value of rate constant highest? So value of rate constant will be highest if the value of activation energy is the lowest. Because activation energy is that barrier which something or some system has to cross in order to find, like from the reactant, if we need to form the product. So there is some another equation which is from the classical thermodynamics, which we'll consider and calculate using that equation. So that equation is so that equation is K, where K is the rate constant, is equals to KB T by H, okay, Q star by QA dot QB and e to the power minus E naught by RT. Okay. Now these terms initially they are new to all of us. So first of all, what is KB? KB is the, just a second, KB is the Boltzmann constant. And its value is 1.38 into 10 to the power minus 23. Okay. And KB is equals to, since I'll just deduce how the KB comes, so KB is equals to R by NA. Okay. Now here R and NA are not so new terms. R is the gas constant whose unit is joule per Kelvin per mole, and The unit of Avogadro number Na is mole inverse. So cancelling these two mole inverse, the unit of Kb comes to be joule per Kelvin. So Kb comes to be 1.38 into 10 to the power minus 23 joule per Kelvin. Okay. Now this we have discussed about what is Kb. Kb is the Boltzmann constant. The second thing is T temperature. Suppose you take the temperature to be 298 Kelvin, which is the normal room temperature we always consider. So its unit will be Kelvin. H, its unit, H is the Planck's constant, whose precise value comes to be 6.626 into 10 to the power minus 34 joule second. Okay, wait, it has just gone out of the board, so this is not necessary part. I'll just rub it. Yeah, so H, its value is 6.626 into 10 to the power minus 34 joule second. Okay. Now how will the maximum value of K come? Maximum value of K will come if I consider this EA, this E to the power entire thing, because as you increase the value of E naught, what will happen to the value of K? If you increase this E naught thing, the K value will decrease since it is in negative exponential. Okay. Is it true or not? Hello?
Yeah.
So, if you increase the value of E naught, anyhow the value of K will increase. Now, what happens if I make this entire value to be 1? Okay, so nothing will be affecting the value of K. And when will this value be 1? This value will be 1 if the value of E naught upon or EA is 0. Okay, so how do we get this? Consider what, in order to find out the maximum value of K, anyway we have to consider that the value of EA will be 0. If you consider it to be 0, what you will do? E to the power minus 0 will anyway it, or you can say just 0. E to the power 0 will come to be 1. Okay. Now this, what are these Q star, Q and QB? For a system, these are the value of partition functions. So, if you consider the value of partition function also to be 1, then what you will get is, just a second. Yeah. So then what you will get is the maximum value of K. So first what I did, first I put just assume that the value of EA is 0 and therefore the value of E to the power minus E upon KT is E upon RT, that will be 1. And then I also considered that in the case Q, this entire partition function is also 1. Now what happens? What we get is K is equals to KB into T by H, and if you put the value of these constants somewhere, you will get the maximum value of K. I would like if you solve this question on your own and just substitute the values, because I have given the values of each of the thing. So, the value of KB is 1.38 into 10 to the power minus 23. The value of T you can take to be 298, and value of H, wait, now I am writing just the value of T. So, it is 298 and 8 Kelvin. Okay, and the second thing is the value of Planck's constant, which I have given here, which is 6.626 into 10 to the power minus 34 joule second. I just want you to put all these values and find the value of K. Let me just see how many people are there in the meeting. Yeah. So, Adrija, can you solve this question?
Yeah, sure.
Just I'm giving you a time of 2 minutes. Just put the values of these constants everywhere and try to solve this question. Yeah, did you solve the question?
Yeah, I solved the answer comes here 6.2 into 10 to the power 12.
Yeah. So it's almost correct. So we'll not go to the exact answer, but here in the question we are supposed to answer the entire thing in the order of something.
It will be option B.
So that's not option B actually, it's option D, sorry, option C, because our rate constant what we are supposed to calculate, that will be in the order of 10 to the power 12. So now you get an idea that how the fastest chemical process, like what will be its time scale, in what orders it will be just happening, that will be in the order of 10 to the power 12 seconds. Now this is just an assumption using which we solve the question, so I'll just repeat what we did so that you get the idea about the thing. So first of all, in order to calculate the rate constant, what we used is one equation that is deduced from the classical theory of thermodynamics, which is Kb into T by H, Q star upon Q into Qb. So Q and Qb are the partition functions, and into e to the power minus E upon RT, where Kb is the Boltzmann constant, T is the temperature, H is equals to the Planck's constant, E into E to the power minus Ea, E is the activation energy upon RT, where R is the gas constant and T is the temperature. Now, first of all, each values I deduced. The first one was Kb, which is also equal to R by Na, and when you just calculate the relation, it comes, sorry, when you calculate from the relation, its value will come to be 1.38 into 10 to the power minus 23. Okay, and its unit will be joule per Kelvin. If you want me to calculate this unit again or this value again, or you can just try to calculate, so you'll get that how did I deduce this, and how just a second, Kb is equals to R by Na. So value of R what we used was 8.314. and value of Na what we used was 6.022 into 10 to the power minus 20, sorry, into 10 to the power 23, 8.314 whole upon 6.022 into 10 to the power 23. Okay, now 8.314, its unit is joule per Kelvin. Okay, I'll write this in some clean place. Yeah, so joule per Kelvin per mole, and the unit of Na was mole inverse, and its value was 6.022 into 10 to the power 23. Okay, now when you divide the entire thing 8.314 by 6.022, you will get the answer in the order of 10 to the power, sorry, yeah, 10 to the power minus 23. Okay, and if you divide this somewhere, you will get the 1.38 into 10 to the power minus 23. These two units mole inverse will be cancelled and joule per Kelvin will be the unit. Now if I say you the temperature is 300 Kelvin or say 350 Kelvin, now you just help me calculate the value of K. Will you do this? Just keep the value of K to be 350. Is it easy for you or you will have some problem in solving this?
We can solve.
Yeah, so yeah, you can just try it once afterwards after the session is complete. So the second thing is, so now you got the answer using all the values, you can just calculate, that will come to be 10 to the power 12. Okay, now the next question will be, first, 40% of light incident on the sample is absorbed. The absorbance of the sample is, there is a spelling mistake here, sorry for that. So 40% of the light on a sample is absorbed. Now absorbance of the sample is, earlier I told you that there is, like, there will be some questions coming in the future which will require this relation which we taught, which I discussed in very brief or very briefly, but now we'll discuss this relation in detail. So first of all, what I will just say is, what is absorbance. So earlier what absorbance was, absorbance is the given in the relation from the Beer-Lambert's law. Absorption is given as epsilon Cl, where epsilon is the molar extinction coefficient or molar absorption coefficient, C is the concentration of the analyte, and L is the path length of the sample. Now this whole relation does not include any term which is related to the intensity, but we need to calculate this in terms of intensity, because now in this question we are given one relation that we are asked to calculate if 40% of the light incident on the sample is absorbed. Now how to calculate this? So just a second, as we discussed here, I have written the relation where A is equals to log of I naught by I, where I naught is the intensity of the incident light and I is the intensity of the transmitted light. Now how to solve this? We'll just discuss this. First, A, absorbance is equals to I naught by I. Okay, and just tell me which term did I forget in writing this formula?
You didn't write log.
Yeah, thank you. So this says you are quite attentive in this class. So first of all, absorbance is log of I naught by I, and I intentionally did not write so that I could see if you are quite attentive or not. So if you talk about the log thing, and since this is a ratio, what conclusion do you come to? Like, does absorbance have any unit or it is unitless? What is it?
It is unitless.
Yeah, okay, that is correct. So absorbance is unitless. Now, absorbance is equals to log of I naught by I. Now, how to calculate what we are asked to from this question? So earlier what we were told that only the 40% of the light incident on a sample is absorbed, then the absorbance of the sample is. So here I'll just say that what to write is, now consider that if I naught is the value of the incident light on the sample, okay, and what is I? Okay, so first I'll write I naught is equals to intensity of the incident light. Okay, then what is I in this case? This I is the intensity of the transmitted light. Okay, what is this I? This I is the intensity of transmitted light. Now I have given you, let me show you this pictorially. This is the sample. Okay, this light I am incidenting, which has the intensity of I naught. This IT is transmitted through this. If you talk about in percentage, let's say this is 100. If you say this is 100, okay, and only 40% is transmitted. This is a different case, although only 40% is transmitted. Now, if I tell you to calculate the amount of light absorbed or the intensity of light absorbed in percentage, how can you calculate it? Just tell me the answer. What will be the IA? What will be the value of IA?
60.
Yeah, exactly. So the total light, as you can say, will never be totally vanished, and IA will be equal to I naught minus IT. Exactly. Is it correct? What did I write?
Yeah.
So 100 minus 40, and this will come to be 60%. Okay, now again recap to the question what we are asked to solve. If 40% of the light incident on a sample is absorbed, the absorbance of the sample is. Now here what we are given is the light incident on the sample that is absorbed. That is what we are given is IA is given to us. Okay, IA is given to us and we have to calculate IT. Now what you will do? If you want to calculate IT, just reverse the formula, and what you will use is IT is equal to I naught minus IA. Got it? Now I naught minus IA. Just turn the pages, and what we are given, 40% of light is absorbed, which states IA is equals to 40. Now what are the things given, or what is the observation given? I naught is equals to, as always, it is 100%, and IA, which is the light absorbed, its intensity, or it in terms of percentage, it is 40%. Okay, so here we'll calculate A is equals to log of, just a second, this is not very proper. Yeah, so oh sorry, so here A is equals to log अरे यार, yeah, log of I naught by I, you can say t. Okay, so I naught, what was it? 100. And what is IT? IT is what we could calculate from this relation is 100 minus 40. Yeah, is it correct? So 100 minus 40 comes to be 60. Okay, so just calculate this. Log of bracket 100 by 60. Okay, and just let you, for convenience, we'll cancel the zeros. Log of 10 by 6. We'll just calculate this. So log of 10 by 6, what is the answer? Can you just tell me, Adreja?
Yeah. 0.2.
Yeah. Can you just repeat the answer? 0 point? Okay, 0.222. Yeah, thank you. Yeah, so now we got the answer, that is 0.222. And if you want to convert this to percentage, can you just tell me how you'll convert this to percentage? Just multiply it by 100 and therefore the answer will be coming in like 22.2. Okay, 22.2%. Okay, so this is the absorbance. Now if you want to calculate the transmittance, there is another relation which I'll just help you to, because the questions will not come directly to calculate the absorbance. You need to know all the things regarding the Beer-Lambert's law and how to calculate the even the transmittance. So we'll go to our next page and we'll just learn how to calculate the transmittance also. Yeah, so transmittance, how is it calculated? First of all, A, as we studied, is equal to log of I naught by I. Transmittance, if any one of you knows, just tell me. If you know, otherwise I will be discussing with you.
Maybe reciprocal of absorbance.
Okay. Yeah, so actually absorbance is the you can say negative log of I by I naught. So absorbance is negative log of T actually. Okay, so this is the value of absorbance. Okay, and if you just compare these two, you will get to know what is transmittance. Just help me how to calculate this. Suppose if you just say that A is equals to negative log of I by I naught. Okay, and transmittance is and absorbance is also negative log of T. So just tell me what is T now.
T is I by I0.
Yeah, exactly. T is equals to I by I0. So this is the value of T. Now if something is given to you, just you can calculate transmittance using this value. Just calculate it, okay. I'll just help you, where I will be the transmitted light. So what is the transmitted light in our case? Yeah, what is the transmitted light in our case? IT was 40%, right? Or IT was 60%, sorry.
So T is coming to be as 0.6.
Sorry?
T is coming as 0.6.
Yeah, so T will come to be 0.6 exactly. Now we'll go to the another question. So so this was just like, this question did not have any options with it. So actually we only calculated the value. So what was the absorbance? That was 0.22, or in percentage it was 22.2%. And this is how we calculated the entire thing. Okay, now we'll go to the another question, which is, what is the dispersing element in modern spectrometer? Okay, now dispersing element in modern spectrometer. Okay, so if you talk about modern spectrometer, just a second. Yeah. So what is the dispersing element in modern spectrometer? So modern spectrometers, what do they comprise, and what is this dispersing element? What they are saying is, these are the small things which we need to understand, and which just revise, because earlier it has already been discussed. So if you go to a schematic diagram or a block diagram of the thing, the spectrometer contains a source of light. Suppose this say is a source of light S. Now, if you can say I have taken a source of light, that is the deuterium lamp along with the tungsten filament, or what we discussed is xenon arc lamp, which is the most advanced, which is more intense compared to the deuterium and the tungsten filament lamp, and which has a broad range of light as well. So there are three options for a source. You can take the deuterium lamp. Okay, for deuterium lamp, which is a source of UV light. So deuterium lamp. The second one will be tungsten filament. So both these are used together, tungsten W or tungsten filament lamp. And the third one is, okay, is this writing not legible? Okay, I'll just write it again because there is a problem. Just a second. Sorry for the inconvenience. I just hope next time we'll not like we are not we do not face these things. So first is the deuterium lamp. I am just writing it with D. Okay, so that it is more proper and legible to you. So first is the deuterium lamp. Second one is the tungsten filament lamp. And the third one is the xenon arc lamp. Okay. So these are the three sources. Now, if you want to just from the source, suppose here is the radiation that goes. Now, at the time, if I want to illuminate my sample is here, I just, for a better resolution, as we studied, the light needs to be monochromatic. It needs to be highly monochromatic. so that if you illuminate the sample you get a very precise resolution, like what is the absorption in that particular wavelength, specifically if you talk about the UV visible spectrophotometer. So if you want to talk about the UV visible spectrophotometer, first of all the sources will be tungsten filament lamp or deuterium lamp, and second thing, what is the most essential element, that will be a monochromator. If I denoted this with T, and the third thing will be a sample holder through which, and the fourth one will be the detector through which you will collect. Normally the detector, I'll denote it with a D. So this dispersing element, which this is component of which part? So first of all, this dispersing element is the component of monochromator. Now what does this dispersing element do? As suggested by the name, the dispersing element helps to disperse the light. Okay, so normally a dispersing element can be a prism, as you okay, a prism which earlier in the initial days which was used to disperse the light, the light which comes from the sunlight or the visible range of light which was used in the earlier experiments to disperse it into the Vibgyor thing. The grating that is in the form of the grating that is in the form of like slits, the grating that is in the form of the curves on the surface, slits that is in the form of a rectangular small slits through which the light can pass, or a curved mirror. Now, so better is if I draw the entire thing so that it is better for you. Most of all, any of these things can be used. So first is the prism, which is not normally nowadays used, that is the prism thing. If you incident the light over this here, it will just reflect towards the normal and then it will be dispersed into the variety of light which we studied. So what is the principle is, if you have the light source which emits from a range of 380 to say 740, you will be able 380 to 740, you will be able to separate these according to their wavelengths, but this thing is not used nowadays. The other thing which can be used is, first of all, this is a grating. What is this? This is just a surface with such type of curvature over this. Now which principle does this include? How is it used? Suppose a light is incident on this like this. This is a solid support. How it will be diffracted? It will be just like this. So according to the angle with which it is diffracted, you can just calculate the wavelength which of what it is. And here you can have a detector, specifical detector for different wavelength. So this entire grating works on the principle of Bragg's law. What is Bragg's law? N lambda is equals to 2d sine theta. Okay. So if you have a known material, if you know the value of D, if you have known the value of N, which is probably 1 all, so you can calculate and you also have the value of theta, because you know the angle with which it is diffracted, and therefore you can calculate the lambda, and this is how the different wavelengths can be separated, different wavelength of light can be separated. So this is the modern advanced grating thing which can be used. Now the other one is slit. Slit is just a rectangular like this portion through which the light can pass, and therefore you can just separate these things, these light according to their wavelengths. So if you want to answer this question, whatever answer would be, it would be better if you just choose the options among these, as I have told you. What are the things, or what can be the dispersing element in a modern spectrophotometer? Yeah. So apart from this, grating and slits, curved mirrors is also one of the option. Like curved mirrors can also be the part can also be used as a dispersing element. Yeah. So now the other question is it is also a type of numerical thing, and I have prepared this. You will be getting some options, or maybe not. You will getting some like this question is to calculate the emission quantum yield if I naught is the intensity of light absorbed and I is the intensity of transmitted light. First of all, I'll repeat the question once again. Calculate the emission quantum yield. What is quantum yield? This will be discussing in the further portions. If I naught is the intensity of the light absorbed and I is the intensity of transmitted light. Okay. So, yeah. So, in order to solve this question, I'll come to this board thing. So, first of all, yeah. What is a quantum yield? Quantum yield is normally denoted by the term phi. What phi is? Phi is the amount of light absorbed upon the total intensity of or the total amount of light incident on the sample. Or in very simpler words, what I am writing, if I is the intensity of light emitted or transmitted by the sample, yeah. So if I is the intensity of the light emitted, EM, I'd note it with EM, emitted by the sample upon the total intensity of the light incident on the sample. Can you just tell me what will be the value, or in which range the value of phi will lie? Because this we have discussed earlier. I have given you a hint already, like what will be the intensity. Will it, okay, I'll just give you one more hint. Can you just predict, will the intensity of light which is incident on the sample be greater or smaller than the value of a light or than the intensity of incident light? Or if you cannot understand, I'll just repeat this question. The intensity of emitted light, will it be greater or smaller than the intensity of the incident light? Is my question clear?
Yes, it's clear. The intensity of the emitted light will be less than the intensity of the incident light.
Yeah, okay.
So phi is expected to be less than 1. It will be between 0 to 1.
Yeah, okay. Yeah, so this is correct. The phi will be always less than 1. Okay. Now, this is quite complicated because IEM I don't have, I naught I don't have. Okay, and what I have is, I'll just tell you, I naught and I. Now, okay, emission quantum yield, if you want to calculate the emission quantum yield, this is the relation. What if you don't have IEM or I naught? How will you write this entire thing? So for this, there is some other relation also which you can calculate, through which you can just use or calculate. So first of all, if you want to calculate IEM, so or the I transmitted, so I transmitted can also be written as IEM is equals to I naught minus I absorbed by the sample. Okay, and one more relation which we used was A is equals to log of I naught upon I. Okay, now here A has no unit, I naught is the intensity of the incident light and I is the intensity of the transmitted light. If you want to calculate I or IEM, these two are the same things. So you can just write log of I naught upon I naught minus I absorb. Isn't it easy? A, B, S. Okay. Okay, I'll just write it more clearly. Yeah. And this is also not very clear actually. So log of I naught whole upon I naught minus I A B S. Okay. Now, if you want to calculate this thing, just let me tell you one thing. Just take it like this is log base 10, okay? And this is log base 10. So you can just take it as 10 to the power A is equals to I naught upon I naught minus I ABS, or else you can take 10 to the power minus A is equals to I naught minus I A B S whole upon I naught. Okay. Nice. Got it? Now I'll write one more thing. From this I'll derive 1 minus I ABS intensity of light absorbed upon I naught. Okay, so this entire thing I have deduced from this only. Now I'll just write it once again in another form. I'll bring this to left hand side, LHS side, IA B S upon I naught is equals to 1 minus 10 to the power minus A. Okay, and then IABS also I can calculate. So IABS is equals to I naught bracket 1 minus 10 to the power minus A. Okay, so this I'll just rub from here. Yeah, okay, write it again. Okay, now if this relation is clear to you, I'll just write like highlight it. IABS is equals to I naught minus bracket 1 minus 10 to the power minus A. Now you see from this relation. Okay, what was the relation? The relation was phi is equals to IEM upon I naught. Okay, and what we could calculate is IABS, or the I absorbed, can also be calculated as I naught into 1 minus 10 to the power minus A. Okay, now what was the relation between the what was the relation from the quantum yield? Yeah, so sorry, just a second. Initially I just wrote one thing wrong. That was I is equals to IEM upon I absorbed. Okay, now it is all clear to you. Sorry for the writing this thing wrong. The quantum yield will be the intensity of the light, will be the ratio of intensity of light emitted upon the intensity of light absorbed. And now I could calculate intensity of light absorbed from I naught into 1 minus 10 to the power minus A. So the entire formula will now become phi is equals to IEM whole upon I naught into 1 minus 10 to the power minus A. So this is the relation. Now I'll give you two questions related to this formula. Okay, by clearing the page I'll just write the entire formula again. Okay, so what is phi? Phi is, so phi for emission and quantum emission quantum yield will be intensity of emitted light upon I intensity of absorbed light, or in other words it will be intensity of emitted light whole upon I naught, means intensity of the incident light, into bracket 1 minus 10 to the power minus a. So this is the thing. Okay, so yeah, so this is the relation. Now I'll give you two questions which you have to solve. First of all, calculate the emission quantum yield if I naught is the intensity of light absorbed and I is the intensity of transmitted light. If you calculate, or if you just deduce the relation again and just tell me in the terms of I and I naught, I'll just write the relation. Okay, just tell me and calculate the relation on your own. Okay, yeah, so just tell me if I have substituted the value of I naught and I is the intensity of the transmitted light, or transmitted you can say I is the intensity of the emitted light. What will be the relation?
Then phi will be I by I.
No, phi cannot be I by I0. Phi is the intensity of emitted light upon the intensity of the absorbed light. So emitted or transmitted, you can write both. So, or they are not always same, like, but you can just say it is the ratio of intensity of the emitted or light upon the intensity of the absorbed light. So if I naught is given to you, you can just deduce it from the relation which I told you, or which we derived. That is not a very cumbersome process. That is quite easy. Phi emitted is equals to I emission, intensity of the emitted light upon intensity of the absorbed light. Got it? Now, intensity of the emitted light upon intensity of the absorbed light, I'll just tell you how did we deduce this. So how we deduced it, right? Like from this relation which we studied earlier. Absorption is equals to log of I naught by I, where I is the value of the transmitted light. Okay, here also I is given. Now if you want to calculate, I is also given as I naught minus I, intensity of the light absorbed. And then if you just remove the things and convert this log a to 10 to the power a and 10 to the power minus a, then 10 to the power minus a is equals to I naught minus I abs, absorbed intensity of light absorbed, upon I naught, and then it will come to be 1 minus I intensity of light absorbed upon I naught. Okay, now if you solve this, bring the terms to LHS and RHS, just shuffle them a bit, you will get the relation 1 minus 10 to the power minus A is equals to I absorbed upon I naught. Now when you calculate this in terms of I naught, you can get the relation, and this is what we have to use there. This is what we have to use here, that phi is equals to IEM. Now in the question you can carefully see that intensity of transmitted light is I. So just replace the value of IEM by I, and I naught is given to you clearly from the starting, and absorbance is not given, but you can write this in this term also. Got my point? Is it clear to you?
Yeah.
Now we'll come to the next question. Now, fluorescence emission spectra does not match the absorption spectra. What can be the possible reasons? Yeah, this is also one of the important questions. Suppose if you have a mixture, if you have a solution Just tell me the name of something which you know does show a fluorescence. Do you know the name of any dye or something which is fluorescent? Okay, so if I just say a name, the name is rhodamine B. So this is the name of a dye which shows fluorescence. Now there is two things, emission and absorption. As you can see from the question, what is it written? Fluorescence emission spectra does not match the absorption spectra. Initially I had told you one thing, that was suppose you have a substance suppose you have something whose solution is like, you have prepared a solution in a respective solvent. So its absorption in that solution will be like this. Okay, this is not very proper. I'll just rub it. Okay, so yeah. Now maybe you will have some question like, what are the coordinates x and y of this spectra? So if you particularly talk about absorbance, here in the absorption spectra, here is the absorbance and here is the wavelength, okay, which is in increasing order from 200 to 800. Now if you consider this, the absorption, let's say, of some substance is, or in the solution, it is in the form of this. This is some range. This is the absorption maxima, which you denote by lambda max. Okay. Now its emission spectra, if you take again, the emission will not be in the same range. The emission will change. The emission will be somewhere here for the same substance. Why? If it emits. The reason for this redshift was some intramolecular or intermolecular quenching or the loss of energy which is causing it to redshift. So this is the entire thing. So this is the absorption spectra which I denote by ABS, and this is the emission spectra which I denote by EM and M. Okay. Okay, this is not very proper. I'll just write it. Yeah. So E, M and M. This is the emission spectra. Why these two do not match? That is because of the intermolecular relaxation. Okay, or intermolecular relaxation, the loss of energy in internal conversion, intersystem crossing, many radiative and non-radiative processes. Now, if this loss of energy, if this coming down to the ground state, this is in the form of radiation, then it is called emission. What our question was, the fluorescence emission spectra does not match the absorption spectra, because for a particular substance or the solution, if you take the absorption and emission, ideally these should come. Like if the absorption is in the particular range, say 380, the emission is in the range of 560 or 540. If you take the emissions after absorption spectra, if you take the emission spectra, and after the emission spectra, if you reverse the process and take the excitation spectra again, that these two should be matching, or your excitation spectra should match the absorption spectra. But if this does not happen, what can be the possible reasons? So for this, the possible reasons can be maybe mixture of many substances, impurity, solid, or excess concentration of the sample. I'll just repeat the options: mixture of many substances, impurity, solid, or excess concentration of the sample. There is a hint, there are many options given in the answers which may be very irrelevant. They cannot be like up to the, like they may not be the options, and like there is no chance for them to be the right option or the correct answer. Now since absorption spectra, this is the characteristic of the compound, okay, and emission is also. So if in your entire mixture or in the solution there are many substances, suppose there is a mixture where one thing is fluorescent, the other thing is non-fluorescent. Now if you take the absorption spectra, you take the emission spectra, and the two do not match. Actually the term here should be excitation. The reason can be there can be a mixture of substances. Suppose you have a known solution whose absorption is 380 nanometer. Now you did not take the absorption spectra, you just took the emission spectra of it, taking the excitation wavelength to be 380 nanometer, and after taking the emission spectra you got the peak. But after taking the emission spectra, if you go back and take the excitation spectra with of the same sample again, and you do not get a single peak, you get multiple peaks. What the reason may be? There is a mixture of the within the solution, there is a mixture of substances which some may be fluorescent, some may be not fluorescent, although they will show some absorption, but they will not show fluorescence. So instead of one peak in the absorption, you will get number of peaks. Now the case may so happen that you get two peaks in the absorption and one peak in the emission, which states that only one of the transition or only one of those two transition is able to show the or is shows fluorescence, not both of them. So uh, X is concentration of sample. In these four options, X is concentration of the sample. This cannot be the answer. Why? Because anyway the concentration is will never affect the uh, matching of the spectra. Although if in your sample you have excess concentration, if in your solution you have excess concentration of sample, it is never ever just suggested to take the excess concentration. If you want to take the absorption or emission spectra, you need to keep an optimum absorption. You need to keep an optimum concentration. It should not be too much or too less. And the third option as given is solid, and this can also not be the option. So according to me, there are two chances, like mixture of many substances which can be fluorescent, which can be non-fluorescent, and the second thing is impurity. So impurity is also one of the reasons which can cause or which can be responsible for this mismatch of the absorption and the emission spectra. Okay, now uh, 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 just since we have some more time, I'll just give you one small question from this formula which we did used. Now suppose I give you the value of I and I naught and the absorbance. Can you calculate emission quantum yield for me? Okay, so I give you the value of I to be 60% and I naught to be 100, and the absorbance in this case will be 0.36. Just calculate the quantum yield. You have 2 minutes of time. So for your sake, I'll just keep the formula on the top. Yeah. So here I've given you three values. What are those? The I have given you I emission to be 60%, I to be 100, and absorption so to be 0.36. Just substitute the values and calculate. Yeah, could you calculate? Or else if you couldn't,
It's coming greater than 1.
oh, okay. Yeah, so I'll just give this question next time, and you just try to solve this question, or else we'll work on it in the next session. So in this session, if you have any doubt, okay, yeah, so we'll just finish the session. Thank you. Thanks for joining the session.